First, a joke. In 2016, the most famous AI engineer on Earth tweeted, 3e-4 is the best learning rate for Adam, hands down.
He was kidding. Mostly. Because this one number decides whether a machine becomes brilliant or brain dead. Watch it happen. For real. Right now. Watch these two machines learn to read. They are identical twins, the same artificial brain, copied down to the last detail. Same wiring, same starting point, same 60,000 handwritten digits to study, same everything, laid out in advance, twice. We train both 15 passes over the data. The first twin learns to read digits it has never seen, 94.8%. The second learns nothing, 10%, the accuracy of guessing. And it is not slow, it is destroyed. We let it keep training, it never moved again. Between these two futures, exactly one thing was different. Not the brain, not the data, not the code. One number. In the first run, it was 2. In the second, 32. That number is called the learning rate. It controls how fast a machine learns, and it is the single most consequential number in machine learning. Pick it well, and a machine teaches itself. Pick it badly, and at the scale of the models you talk to every day, more than $100 million of computer time can produce a machine that knows nothing. This film is about that one number, and here is the deal it makes with you. We start where a 10-year-old can follow, a story about walking downhill in fog. Then, level by level, we go deeper. Real experiments you can rerun, then the mathematics, then the actual code, line by line, then every kind of learning rate there is, until at level 6, we are reading the real flight plans of the largest machines ever built, where nobody gets a second try. Climb as far as you like. Every level is a place to stand. Let's turn the dial.
Inside AI, the learning rate. How fast should a machine learn? Level 1. No math yet. A story. You are standing on a hillside, at night, in fog, so thick you can see nothing at all. Somewhere below you is the bottom of the valley, and you must get there. You can't see the valley, but you can feel through your feet which way is downhill. So you walk, feel the slope, take a step that way. Feel again. Step again. Now, the only decision you actually control, how big should each step be? Tiny steps, and you will get there in a week. Confident steps, and you stride down in minutes. But take enormous leaps, and something silly happens. You jump clean over the valley and land on the opposite slope, higher than you started. Leap back, higher again, forever. That step size has a name, and you have just understood, completely, the number this film is about. Because this, from episode 2, is how a neural network learns. The valley is wrongness. The deeper you go, the fewer mistakes the network makes. The fog is real. The network never sees the whole landscape. It can only feel the slope where it stands. That slope is called the gradient, and how the network feels it is episode 3's story. And the step. New knob value equals old knob value minus the learning rate times the slope. The slope chooses the direction. The learning rate, eta, the little Greek letter, decides how far you commit. One more thing, and it should bother you. The network has 13,002 knobs, each on its own hillside, some steep, some nearly flat. And one single dial scales every step they all take together. In episode 2, we set that dial to 2.0. And I never told you why. Time to pay that debt. Starting with where the dial actually sits, in the real program.
Before we turn anything, meet the machine properly, in numbers, because those numbers are about to be everywhere. If you've seen episodes 1 and 2, this is 30 seconds of a refresher. If you haven't, this is everything you need. The machine reads handwritten digits. A digit to a computer is a grid of pixels, 28 by 28, 784 little squares, and each square is just a brightness, 0 for black, 1 for white. Those 784 numbers flow into a first layer of 16 neurons, then a second layer of 16, then 10 outputs, 1 for each digit, 0 through 9. Whichever output lights brightest is the machine's answer. Every connection carries a knob, a weight, that decides how much one neuron signal matters to the next. Count them with me. 784 times 16, plus 16 times 16, plus 16 times 10, 12,960, plus 42 little nudge knobs, called biases, 1 per neuron, 13,002. That is the entire machine, and training means nothing more than finding good values for those 13,002 knobs. And hold one thought, because everything ahead depends on it. None of these numbers is a law of nature. No network has to have 16 neurons or 13,000 knobs. We chose this machine, back in episode 1, small enough to see inside. Build the layers wider and you get millions of knobs. The machines waiting in level 6 have 405 billion, 31 million times our little reader. And yet, and this is the point of the whole film, it is still one bag of knobs, one slope per knob, and one dial. The sizes change, the story doesn't. The digits are real, 60,000 of them, handwritten decades ago by American Census Bureau employees and high school students, gathered into the famous MNIST collection. And 10,000 more stay locked away as the final exam, digits the network never trains on, so every score in this film is honest. Wrongness, the thing we roll downhill on, is one number, how far those 10 outputs land from the right answer, averaged over digits. That's the whole cast. 13,002 knobs, 60,000 digits, one dial.
Let's watch one real step, the first step of episode 2's training run, on its actual first batch of 100 digits. The network computes 13,002 slopes at once. Here they all are. The steepest one, 0.247. It belongs to the output neuron for the digit 2, which at this moment is confidently wrong. The median slope, 0.000156. Most of the network barely knows which way to move yet. Now the learning rate does its work. Multiply. At eta equals 0.001, the boldest weight in the entire network moves by 1/4 of a thousandth. At eta equals 2, episode 2 setting, it moves by about half. And at 128, that same weight is thrown by -31.65 into a region where a sigmoid neuron outputs a number so close to 0 that the difference is beyond the reach of ordinary arithmetic. Same slope, 3 different futures. And all of this, the walk, the slopes, the multiply, is, in the real program, astonishingly small. Let me show you the whole thing.
Level 1 ends with the actual code, because you can read it, all of it, 8 lines. Line 1, make the 13,002 knobs, random, from seed 1847. So every run in this film starts from the identical network. Line 2, repeat 15 times. Each full pass over all 60,000 digits is called an epoch, Line 3, shuffle the digits like a deck of cards. Line 4, deal them out, 600 hands of 100 digits each. Each hand is called a batch. Line 6, for this batch, compute all 13,002 slopes at once. That single word, grads, is episode 3, and tonight we take it on faith. And then, line 8, knob minus equals eta times slope. That's it. That is the line where every neural network on Earth learns. The fog walk, the dial, the step, in 5 characters of arithmetic. Everything else is bookkeeping. Every experiment you are about to see is this exact program, rerun with one change, the value of eta. Level 2, we turn the dial hard in both directions and watch what really happens.
8 training runs. Everything identical. The network, the starting weights, even the order the batches arrive in. The only thing that changes run to run is the dial, from 0.001 multiplying up by roughly 4 each time to 128. 15 passes over 60,000 digits each, then the same final exam, 10,000 digits the network has never seen. Here are the results, in order. 13.5%, 24%, 88.4, 93.6, 94.8, 94.3, 10.1, 10.1. Look at the shape of that. It rises, it flattens into a broad, forgiving plateau, and then it does not decline politely. It falls off a cliff. Every part of that shape has a reason, and each one teaches you something real about training. Let's walk it, left to right.
Eta equals 0.001. After one full pass over 60,000 digits, 600 parameter updates, 1 per batch of 100, the network scores 9.8%. Guessing. After 15 passes, 13.5. It is learning, technically. Every step moves downhill. The mathematics is flawless. Nothing will ever go wrong with this run. It will also take something like 1,000 epochs to reach what eta equals 2 reaches in 5. And this is the failure mode nobody warns you about, because it doesn't look like failure. The loss goes down. The curves point the right way. Everything is fine. Forever. Slowly. In a lab that costs patience. At the scale of a frontier model, where a single training run occupies tens of thousands of processors for months, too small is not safe. It is the most expensive way to fail. You pay for the whole mountain and only climb the first 100 meters.
From 0.1 to 8, the dial is forgiving. 80-fold range, and every run lands between 88 and 95%. But watch the speed, because the plateau is not flat in time. After a single epoch, eta equals 0.1 has reached 12%. Eta equals 2 is already at 88.7. Same network, same data, one epoch. One of them is nearly done, and the other has barely woken up. That's the real reason practitioners fight for this number. Near the top of the plateau, you learn many times faster, and compute is money. And now you know why episode 2 used 2.0. Not wisdom, not theory. We ran a sweep exactly like this one, and 2 sat near the top of the plateau, fast and comfortably far from the edge. That is honestly how this number gets chosen everywhere, measured, not derived. But the edge is where it gets interesting. Between 8 and 32, 4 times bigger, something breaks.
Eta equals 8, 94.3%. A fine run. Eta equals 32, 4 times bigger, 10.09%.
flat. From the first epoch to the last, the line does not move. And look at the cost. The wrongness number the network is supposed to be rolling downhill. 1.0000. Frozen. 15 epochs. 9,000 parameter updates. Each one dutifully computing 13,002 slopes. And stepping. And the total effect is nothing. This is not a slow run. This is not an unlucky run. Something happened to this network in the first moments of training. And whatever it was permanent. Let's do the autopsy.
Here's what the big step did. It threw the weights so far that the neurons saturated 62% of the hidden layer, pinned hard against 0 or 1. At 128, 93%. Saturated means this: each neuron is like a dimmer switch, and these have been twisted so violently they're jammed at full off or full on. Remember the sigmoid shape from episode 1, an S-curve, steep in the middle, flat at the ends. A jammed switch sits on the flat part, and flat means the slope is 0. And the update rule is step equals eta times slope. 0 slope, 0 step, no matter how large eta is. The network can no longer feel its own wrongness. The gradient, the signal that carries which way is downhill, has died at the source. Gradient descent is still running. It's just multiplying eta by 0, 9,000 times over. Meanwhile, the weights themselves have exploded, 3.5 times the healthy run size, huge, confident, and wrong. That's the personality of this failure, and it's worth saying plainly, the too big network is not confused, it is certain. Modern language models fail at the cliff differently. Their numbers overflow and the loss spikes to infinity. We'll see that at level 6. But the geometry of why there is a cliff, that we can state exactly. It takes one parabola.
Level 3. The math. And we take it slowly because it is one line. Take the simplest landscape there is, a marble in a round bowl. In mathematics, that bowl is a parabola. Cost equals x squared, where x is just how far from the bottom am I. The slope at any point is 2x, steeper the further out you are, flat at the bottom, which matches the bowl you're imagining. So one step of our rule takes x to x minus eta times 2x, and gather the terms. That is just x multiplied by 1 minus 2 eta. Stop. That's the whole story in one factor. Each step multiplies your distance from the bottom by 1 minus 2 eta. Eta small, the factor is just under 1. You creep closer, a few percent per step. 0.9, 0.81, 0.729. Eta equals 0.45, the factor is 0.1. Each step wipes out 90% of your error. 1 step, 0.1. 2 steps, 0.01. Nearly perfect in 3. Push further, 0.95. The factor is negative. You leap over the valley to the far side, back again, overshooting each time but shrinking. And at 1.05, the factor is minus 1.1. You overshoot by more than you came. Watch, minus 1.1, plus 1.21, minus 1.33, crowing, forever. The boundary is exact. Eta equals 1. Below it, any eta converges. Above it, every step makes things worse. The cliff isn't a metaphor, it's arithmetic.
One more turn of the idea and the cliff is fully explained. Make the parabola narrower, multiply by a bigger number, and the critical eta shrinks. The rule, the critical learning rate, is 2 divided by the curvature. Sharp, narrow valley, small steps only. Broad, gentle valley, big steps are safe. Now,
Our network's cost landscape is not one parabola. It's a surface in 13,002 dimensions. And here is a real two-dimensional slice of it, measured in episode 2. Look, narrow in one direction, broad in the other. Every direction has its own curvature, its own private speed limit, and the single dial has to obey the strictest one. The narrowest valley anywhere in 13,000 dimensions sets the ceiling for the entire network. That's why our cliff sits where it sits. Somewhere between 8 and 32, this landscape's sharpest direction gets overstepped, the weights fly into saturation, and the whole thing dies. Which raises the practical question. You have one training run and one dial. How do you find the edge without paying for 8 full sweeps like we just did?
There's a beautifully cheap trick, published by Leslie Smith in 2015. One training run. Start the dial absurdly low and raise it 2% every single step, so it climbs the whole range exponentially while the network trains. Plot the loss against the current ETHA. Watch what our network draws. On the left, high loss, the crawl, steps too small to make progress. In the middle, the loss falls and keeps falling, the plateau. The lowest point lands near 11. And past it, the curve turns and then explodes. By 300, the run is worse than where it started. 2 honest footnotes, because the series shows its work. The lowest point is not the place to train. A rate you can visit for 1 step is not a rate you can live at for 15 epochs. Our sweep died at a sustained 32, even though a passing 300 was survivable for a moment. The rule of thumb is, train well left of the minimum. And second, notice this one run, costing minutes, told us the whole shape the 8-run sweep told us, the edge of the cliff, for the price of 1 pass. But everything so far assumed the dial is set once and left alone. The obvious next question, why would the best step size at minute 1 still be the best step size at the end?
2 reasons the dial should move. First, geometry. Early in training, you are far from any valley. Long, confident strides are exactly right. Near the end, you are inside the valley, and the same stride now steps over the minimum, back and forth, forever. Second, and deeper, noise. Remember from episode 2? We don't compute the true slope. We estimate it from 100 random digits at a time. Each batch points slightly different. With a constant learning rate, that randomness never averages away. The network jiggles around the bottom of the valley at a radius set by eta and stays there. The cure is old, older than any neural network that ever worked. In 1951, Herbert Robbins and Sutton Monroe, studying how to find the answer when every measurement is noisy, proved the schedule that works. The steps must shrink. Slowly enough that their total is infinite. You can still travel any distance you need. Fast enough that their squares sum to something finite. The jiggle dies out. Start bold and careful, and you get both speed and precision. Everything modern, every decaying schedule inside every large model is a descendant of those 2 lines. So let's test it. Same network, same budget. 4 ways to move the dial. 30 epochs, same seed, 4 schedules. And notice first how little a schedule is in code. 1 function each. Step number in, learning rate out. The training loop from level 1 just calls it before line 8. A constant 2. A timid constant, 0.2. A step schedule, 2 divided by 10 late in training, divided again near the end. And a cosine, the smooth glide from 2 down to 0 along the gentle first half of a cosine wave, that half the field uses by default. The results, 95.2, 93.4, 95.1, 95.0. And this series shows you real numbers even when they're undramatic. On this small network at this budget, a well-chosen constant is not beaten by anything. The valley is forgiving. The run is short. The jiggle is smaller than the remaining distance.
Robbins and Monroe's cure treats a disease this patient barely has. But look at the row that lost, the timid constant, down almost 2 full points, the largest gap in the table by far. The expensive mistake wasn't skipping the schedule, it was setting the dial low. Hold both of those thoughts. Because at scale, the ledger flips. Trained for 300 billion tokens instead of 2 million steps, 2 million digits, and the noise floor becomes the whole battle. GPT-3 glides its learning rate down cosine style over 260 billion tokens to 1/10 of its peak, and essentially every large model since does the same. The schedule earns its keep when the run is long. And once the field realized the dial could be a function of time, it drew every shape you can imagine. Here's the family portrait.
The family, left to right. Constant. One number, set and forgotten. Fine for small networks as we measured. Step. Hold, then divide by 10 when progress stalls, then divide again. The staircase that trained a decade of image networks. Cosine. The smooth glide to zero, borrowed into deep learning in 2016, and now the default decay of the GPT and Llama lineages. 1 over square root of time, the long, patient tail the transformer shipped with. Cyclical. Up and down in triangles, forever. A strange one, but you already met its inventor. Leslie Smith's range test from level 3 is this idea pointed at measurement. Warm restarts. Cosine down, then snap back up and glide again. A sawtooth that periodically shakes the ball loose to find a better valley. 6 shapes. And all 6 are honest descendants of Robbins and Monroe. But look at the 7th, the one every modern language model actually flies. It decays like the others, yes, but it does not start high. It starts at 0. We have spent an entire film establishing that the learning rate is how fast you learn, so a schedule that begins at 0 should offending. The explanation is the single best experiment in this film.
Here is the dead run again. Eta equals 32, 10.09%, flat forever. Now run it once more with a single change. For the first 3 epochs, ramp the dial linearly from 0 up to 32. Then leave it there for the remaining 12, exactly as before. Watch. 93.2%. The same peak learning rate that destroyed this network, this seed, this data, is now training it almost as well as the best run in the film. That ramp is called warmup, and this is why every large language model you have ever used began its training with one. The fragility is at birth. At step 0, the weights are random, the outputs are nonsense, and a handful of slopes are enormous. Remember the histogram. One weight demanding a step 1,000 times bigger than the median. Full-size steps at that moment hurl the network into the saturated wasteland we autopsied, and there is no way back. But given 3 gentle epochs, the weights organize, the wild early slopes calm down. The landscape around the ball becomes the kind where big steps are safe. Warmup entered the modern playbook in 2017, when engineers at Facebook training with giant batches found they needed it. And the same year, quietly, in the paper that changed everything, which is where level 6 begins. But first, we've been pretending one dial can serve 13,002 knobs. Time to stop pretending.
Look again at the slopes from scene 4. The steepest is 1,500 times the median. One dial must serve them all. Set it high and the steep weights overshoot. Set it low and the flat weights, most of the network, starve. Every setting is a compromise, and the compromise has been the quiet villain of this entire film. The cliff, the crawl, the warm-up, all of them are one dial problems. So what if every weight had its own learning rate, its own private dial, tuned automatically, continuously, by the training run itself? That idea, plus about 4 lines of algebra is the most used optimizer in the history of machine learning.
Atom, published by Diederik Kingma and Jimmy Baugh in 2014. For every single weight, it maintains 2 running averages: the recent slope, which way and how hard this weight has been pushed lately, and the recent squared slope, how large this weight's pushes typically are, regardless of direction. The step it takes is the average slope divided by the square root of the average squared slope. Stop and feel what that division does. A weight whose slopes are typically huge gets its step scaled down. A weight whose slopes are typically tiny gets its step scaled up. Every weight now moves a step measured in units of its own typical slope. 13,002 private dials tuned continuously for free. And in code, the whole idea is 3 lines. M gets 90% of its old self plus 10% of the new slope. That's the recent slope, a moving average, the way a share price gets smoothed. V does the same to the slope squared, and the step divides one by the root of the other. That's Atom. Level 1's line 8 replaced by these 3. Nothing else in the training loop changes. The global alpha that remains is a different kind of number. Not how far, but how far relative to typical, which is why its good values live near 0.001, 1,000 times smaller than our SGD dial, and why the same defaults work on wildly different networks. We ran it. On our network, at the same budget, alpha of 0.01, 94.3. 0.001, the paper's default, untouched, 93.7. Atom did not beat our well-tuned SGD, 94.8 still stands. Read the fine print of the field and you'll find that's typical. Atom's gift is not the ceiling, it's the floor. Every setting we tried just worked, on a dial that for SGD spans a cliff. That robustness is why it, in its modern form, Atom W, trains essentially every large language model. The price, 2 extra numbers stored per weight. For us, 26,000. Remember that ledger? At level 6 scale, it becomes 800 billion. And the meme. The meme.
In November 2016, Andrei Karpathy tweeted, 3E-4 is the best learning rate for Atom, hands down. He was joking. He said so later, a little desperately, as the number spread through the field's folklore. But the joke had teeth, because Atom's normalization is exactly what makes one magic constant almost plausible. In units of typical slope, wildly different networks really do want similar steps. And then, 7 years later, Meta published the recipe for Llama, the model family half the open source world is built on. And there it is, in Table 2, the learning rate for the 7 billion parameter model, 3.0 times 10 to the minus 4, hands down. The joke became the spec sheet. But is the joke number actually any good? This series has one way of answering questions like that. Build the machine. Run it.
A language model is just our fog walker with a different exam. Instead of reading a digit, it reads 8 letters of a story and guesses the letter that comes next. So we built one, 37,000 knobs, small enough to train on this machine in about 1 second. And its textbook is the real text of Alice in Wonderland. Its wrongness has a lovely unit, surprise. Untrained, it is 5 bits of surprise per letter, pure guessing across the alphabet. Now sweep the dial and read what each machine writes afterward. Alpha, 3E-5, alphabet soup. It has barely learned that spaces exist, 3.7 bits. 3E-4, the meme number, word-shaped babble, wot the chiquilaire, 2.9. 3E-3, the chord you know, said to be, almost English, 2.6 bits, the best in the sweep. And 3E-2, hotter still, worse again, but alive. Look at that dial strip. No cliff, no corpse. That is Atom's floor from level 5, holding on a completely different machine. And one thing more,
the loveliest measurement in this film. Our tiny machine's best dial was 3E-3. GPT-3's smallest model, 3,000 times bigger, 6E-4. Its biggest, 6E-5. Line them up. The smaller the machine, the hotter its dial runs. You have just watched one law stretch across 7 orders of magnitude. Time to climb to the top of it, where the dial stops being a knob you tune and becomes a flight plan.
2017. 8 researchers at Google publish Attention is All You Need, the paper that introduces the transformer, the architecture inside every modern language model. Episode 5 tells that story. Tonight, look only at section 5.3, where they tell you how they trained it, and notice that it is not a number, it is a formula, a recipe with 3 instructions. 1. Warm up. Climb from 0 for the first 4,000 steps. 2. Glide down, 1 over the square root of time, forever. 3. The wider the model, the smaller the whole thing. Bigger machine, gentler steps. The curvature law from level 3, written by people who had never seen this film. Everything this film has built is sitting in that one line. The warm-up against the violence of birth, the decay against the noise. The peak bowed to the sharpness of the landscape. From here on, no frontier model would ever again train at a constant learning rate. The dial had become a schedule, printed in the paper. And as the models grew 1,000-fold, the schedules grew stranger, and the peak crept steadily, revealingly, down.
2020, the GPT-3 paper, Table 2.1, 8 models from 125 million parameters to 175 billion, and for each one, printed like an ingredients label, its learning rate. Read the column downward. 6. E minus 4. 2.5. 1.0. And for the full GPT-3, 0.6 times 10 to the minus 4. The model grew 1,400 times larger, and its learning rate shrank to 1/10. There is our level 3 law, wearing a lab coat. Bigger networks carve sharper valleys, and the sharpest direction sets the speed limit. The wider and deeper the model, the more carefully it must step. Meanwhile, read the neighboring column. As the learning rate fell, the batch, the number of tokens averaged into each slope estimate, grew from 500,000 to 3.2 million. Those 2 columns are holding hands, and the reason why is our last piece of theory, measured, of course, on our own little network first.
We ran the grid. 3 batch sizes, 5 learning rates, same budget in epochs. Watch the best dial setting move. Batch of 10, best ETA, 0.8. Batch of 100, 3.2. A cleaner slope estimate, 100 digits averaged instead of 10, is quieter, and a quieter signal can be trusted with bigger steps. That's the handshake in GPT-3's table. Grow the batch, raise what the learning rate can be. The engineers at Facebook wrote it as a rule in 2017, multiply the batch by K, multiply the learning rate by K, and wrote it to ImageNet in 1 hour, with warmup invented along the way to survive the first epochs. But our grid holds a warning too. Batch of 1,000, same 3 epochs, 70%, starving, because the same epochs now contain 10 times fewer steps. 180 parameter updates is not a training run. Big batches don't just permit bigger steps, they demand them, or you pay in progress. Frequency, size of step, quality of estimate. 3 dials, 1 budget. Now you can read a frontier training recipe the way a pilot reads a flight plan. So let's read a real one.
This is the published learning rate schedule of Llama 3, 405 billion parameters. The actual plan its training followed for months. Read it left to right. A linear warm-up, 8,000 steps from 0 to the peak, and the peak is 8 times 10 to the minus 5. Feel how far the dial has come. Our little network trained at 2, GPT-3 smallest at 6e-4. This, 25,000 times more parameters than GPT-3 smallest, steps 1,200 times more gently still. Wait, let me say the honest version. 8e-5, less than a seventh of GPT-3 175's rate, on a model over twice its size. The shrink continues, model by model, year by year. Then the long dive, a cosine glide over 1.2 million steps, down to 1% of the peak. Robbins and Monroe's 1951 conditions, drawn in silicon. And underneath, the other dial moving in concert. The batch starts at 4 million tokens per step, deliberately small and noisy cheap while the network is fragile, doubles to 8, doubles again to 16 million as training stabilizes. Warm up on both dials at once. Every idea in this film is on this one chart, sized at 405 billion parameters and 15.6 trillion tokens. And even flown this carefully, at this scale, sometimes mid-flight, something snaps.
Google's Palm, 540 billion parameters, 2022. The team reported that during training, about 20 times, the loss, descending smoothly for weeks, suddenly spiked. Not our sigmoid paralysis. At this scale, with these architectures, the failure is faster and stranger. A step lands wrong, activations blow through the range of 16-bit numbers, and wrongness explodes upward in hours. Gradient clipping, the seatbelt that caps any single step's total size, standard on every large run, was on. The spikes came anyway. And here is the detail that tells you how strange this frontier is. The fix was not an equation. It was a ritual. Rewind to a checkpoint about 100 steps before the spike, skip a few hundred batches of data, and continue, and the spike does not come back. Replay the very same batches from a different point in training, and nothing happens. It isn't bad data. It's a conspiracy between the data and the optimizer's momentary state. 13,000 dials, scaled to a trillion, catching a gust at exactly the wrong moment. At the frontier, the learning rate is not a hyperparameter you set. It's a system you operate, watched by on-call engineers around the clock for months. Which leaves one last question, maybe the most expensive question in the industry. On a machine that costs 9 figures to train once, how does anyone dare choose these numbers at all?
You measure small, and you transfer. The result that made this possible is from 2022, a reparameterization called mu-p from Greg Yang and collaborators, with a property that sounds too good to be true. Set the network up in the right coordinates, and the best learning rate stops depending on the model's width. Tune the dial on a 40 million parameter proxy for pocket change. The optimum carries over to the multi-billion parameter version unchanged. In their experiments, hyperparameters moved from a model of 40 million parameters to one of 6.7 billion, nearly 200 times larger, and beat the settings the big model had been published with. Cerebras trained a whole open model family this way and printed the method in the paper. How the very largest closed labs set their dials is not public, but small proxy transfer in some form is how the field now thinks. And step back, because the arc of this film just closed. The learning rate began in scene 3 as the humblest thing in machine learning. One number multiplied against a slope. It ends as a discipline, measured on small networks, scheduled like a flight plan, stabilized by rituals, transferred by theorems. Because at the top, the dial gets one turn.
2 networks, 1 number. 94.8 against 10.09. And now you know the whole story between them. The crawl, the plateau, the cliff. The exact arithmetic of the edge.
The schedule that starts bold and ends careful. The warm-up that resurrects the dead. The optimizer that gives every weight a private dial. And the flight plans, rituals, and theorems that set one number for machines that cost more than a skyscraper and get one chance to be born. But this entire film rests on one assumption we never questioned. At every step, we simply had the gradient. 13,002 slopes, one per knob, delivered instantly, as if wrongness itself could reach back through the network and tell every weight its share of the blame. Computing all of them in one backward pass, at any scale. That is a single algorithm. It was worked out for neural networks in 1986. It runs unchanged at its core, inside every AI you have ever used. And almost nobody can explain it. It's called backpropagation. That's next time. Inside AI.